Howdy, everybody. Hope you're doing well wherever, whenever you are. We have a weird day today. I lost the recording kind of part way through. Um, well, I'll explain what happened in a minute. But anyway, you probably didn't want to watch most of it anyway because it was 2 hours of me fumbling around. But yeah, we were 2 hours in and I lost the recording. So sorry about that. I'll try and walk you through the steps. So let's see. With that, let's just get started with the day. I don't even remember what I talked about beforehand, so I'll read the problem and then we'll just continue forward. So this one is an elephant named Joseph, and Joseph turned out to be helpful. The elephants contact you over a highly secure emergency channel. Back at the North Pole, the elves are busy misunderstanding white elephant parties. Each elf brings a present. They all sit in a circle, numbered starting with the position 1. Then, starting with the first elf, they take turns stealing all the presents from the elf to the left. An elf with no presents is removed from the circle and does not take turns. For example, with 5 elves, numbered 1 to 5, so looking like this, so 1 takes from 2, and then 3 takes from 4, and then 5 takes from 1. Then you only have 2 and 4 left. So, you only have 3 and 5 left. 3 takes from 5, so 3 wins in this position. And then it says, who wins if there's this many elves? And my answer was this, which is 3 million. So my answer was, or my puzzle input was 3 million, which was a lot. So anyway, that's the problem. The idea is you have a circle. Everyone's going to steal presents from one after the other, or from the person next to them, and you remove those from the list. Okay, so for part 1, I did actually find a semi-naive solution to this. Well, it was actually the naive solution. I just followed the rules at 3 million, and it seemed to solve it in like, I don't know, it was like 50, somewhere on the order of 50 milliseconds. I could probably do it again if I really needed to, but I'm not. I'm like 2.5 hours into this thing, so I'm probably not going to do it again. But the idea is I basically just did I start with a list of 3 million elements, whatever, 3.01 million elements, and then I would only keep half of them. And the trick that I noticed was, so in each round you remove the even ones, so you only keep the first one, right? So imagine breaking these into chunks. So in this case, I would chunk 1 and 2, I'd keep 1, chunk 3 and 4, I keep 3. So I could basically do that, and so like basically I knew I halved it, and then the only additional thing I needed to do was know if 1 should be a part of it. And that turns out to just be if it's even or odd, right? So if it's an odd length, then I would delete the first one. And so I think the way I implemented it was I did windows and then I mapped it. And beforehand, though, I calculated if it was even or odd. And if it was odd, then I skipped the first one. So you could imagine the way the algorithm work is I'd get 1, 3, and 5 in my iterator, but then I would skip 1 because I was odd. And so now I only have 3, 5. And now I just keep 3, and then I've solved it. And so again, that it only took it was definitely less than 100 milliseconds. I don't remember the exact amount. Anyway, so that was part 1. The naive approach worked, so I didn't try any further. I think I had solved it in like 15 minutes, part 1, in about 15 minutes or so, including reading the problem. Okay, so part 2, what does it say? They're like, oh, we've gone through the list and we actually don't like the way it happens. We want elves to steal presents from the person directly across the circle. So like the idea is if there's, and then it says if there's 2 elves, choose the one on the left. And that's just that's a simplified version of you just divide by 2, you do integer divide by 2, and you'll get the floor, right? But if you're doing other divides, you need to get the floor of it, right? So like 5 divided by 2 should be 2, if that makes sense. And the idea is you just keep going around in a circle and slowly doing that, right? So they give you an example right here where, 1 is between 3 and 4, so it removes 3. Now it looks like this, and it's 2's turn, so it removes 5. Now you have this, it's 4's turn. 4 removes 1, and then 2 removes 4, and 4, so 2 is the only thing left, so it wins. And then this is where I'm up to 2 hours now. And the reason why it broke was I implemented a naive solution to it. I'm like, okay, well, I'll just try it and I'll let it run while I try and figure it out. Apparently there's something wrong with my computer because it just like gave up the ghost. So I wasn't paying attention to CPU temperatures or anything like that, but it's possible that while it was running, it hit some hotspot, or I honestly don't know what's happened. I think this is the second time this has happened when I've been doing a video. So I'll just have to pay, I may have to start paying more attention to what's happening. Anyway, yeah, I don't know if it's my power supply or like, maybe I need to go check and make sure, my thermal paste is properly applied. I don't know, all kind of that stuff. I build my own computers, so I'll have to check it out and play around and see what it looks like. Anyway, it crashed. As it was running. I'm running it in the background just to see, like, will it ever get an answer? Maybe it will in like 100 years or whatever. I don't know. And if it does, then I can, I'll just answer it and then I'll find an efficient solution. But it wasn't it had been running for like 2 hours, just to be clear. Not totally 2 hours, but somewhere in that order. And so I'll show you the naive one. This is what it looked like for part 2. Oh, I should show you. No, I won't show you part 1 yet. So here's what part 2 looked like. The idea is make your list of elves and keep track of whose turn it is. And then while there's more than one elf, we just check, we just basically remove whoever's turn it is, the person across from the row. And you have to do a little math here, right? Is like you say, okay, well, I know whoever's turn it is plus this divided by 2 modulo the length. That gets you like where they are, right? Because it could wrap around, if that makes sense. That's why you do the modulo. And so that's the person to kill, and you remove it. I had a subtle bug, though, I had to figure out when I was like debugging it for like small values. And I actually did it by hand. I think you may have seen that already. So here's my whiteboard. I did some of them by hand so I could see what they look like. So you can see, like, on an order of 6, 3 wins, and on 9 wins. And I knew the 5 was 2. So I figured based on those 3, I could get them all. I picked 9 because I think it was the first one that looped over into the next turn type thing. Or I don't remember why I picked 9. It had something to do with this evaluation. So the idea is you figure out who you want to remove, but if you've killed someone, if kill is greater than turn, like you've killed someone ahead of you, you can increment, like you can move to the next person. But if you've killed someone behind you, you don't want to increment. The reason and the issue is like if you've killed someone behind you, because it's like wrapped around the thing, right? It's circular, remember? So my thinking that where I was going with this was, if you've killed someone before you, the next turn is actually now the person in the thing, because you've removed someone before you, and so now the turn shouldn't update essentially. And then if we ever wrap around, then we want to set our turn back to 0, right? We want to go to the 0th one. Anyway, this is all to say that this actually solves the problem. And it got to here. And so here's where I'm at right now. I think I'm actually close to this because there is a pattern here in the things that I think we can solve. And so that's what I've been doing here. When I was looking, I should say, when I was looking for the patterns, I found a better solution to part 1. And I think I had mentioned this, the Joseph thing happened to be relevant. I was like, is there a pattern to this? Have we seen this before? So I did some Googling, and it turns out it's the Josephus problem. So the Joseph, I think, was the hint here. In the Josephus problem, it is this exact problem, except they call it you kill the person next to you is the way it works. At least for k equals 2, right? This is the one we're doing where you kill the person next to you. And it turns out there's a formula for it. It is, where's the formula? It's like 2L plus 1, where L is the highest is 2 to the M, where M is less than I or so. I can't find less than, yeah. No, I can't. Well, I mean, I guess I can just show it to you. It's this right here. You basically just find the highest order bit. That's your like 2 to the N. And so you basically, your L is remove that from the input. So like, say for example, for part 1, say this is 5. 2 to the highest order bit in 5 is the 4 bit, right? So you're gonna do 5 minus 4 is 1, and then you're gonna 2 times 1 plus 1 is 3, which I believe is the answer to the problem, right? In the original one, the answer was 3. Yeah. Okay. So that's how you solve it. Super fast. So just to be clear, I had done the naive approach, and then I was working on part 2, stumbled upon the Josephus problem. It led me to part 1, solving it for part 1. I can't find anything in here though that's related to the updated problem. But if you read through this, and we read through it in the 2-hour version, I mean, we glazed through it. I didn't read it out loud, but I read through it. What you notice is there's patterns, right? And the reason the 2 to the N is important is because it's where it resets. So notice it resets at 4, then at 8, then at 16. So it's resetting at 2 to the N's. So for part 2, I said, okay, well, why don't I start spitting those out? And so I did that. Maybe I should remove my K first so you can see how I got where I'm at. So if I do it this way, you can see there is also a pattern here, but it's not 2 to the N, it's 3 to the N. So it resets every 3 to the N. The idea being, if the answer is 3 to the N, the next one is 27, then the winner is 3 to the K, I should say. The winner is K. No, the winner is N. How do I say this? If it's a power of 3, the winner is N. That's probably the way to say it. So what did I do is now I'm like, this is where I'm at. I've been looking at patterns with this. So K is this is me figuring out what the what the power is. So if let me pull up my whiteboard is. it's like what I'm looking for is the 3 to the k that is associated with n. So I want to find some 3 to the k that is less than or equal to n. Which is, so you can see that's what this is, k, this is n, this is k, and this is the winner. And so you can see what's happening, and where I'm at is there is definitely a pattern. Obviously 9 wins because it's the thing, but then for all of the 9 patterns, look what happens. It increments by 1 until I get to 3 to the k, I should say until I get to 9. What is k? Is the first k is the like what's left of, it's not this, so I need to erase this. I don't even know how to do that. It's not this. What I'm looking for is some k where it is some 3 to the, I don't know, p, where k is less than n. I don't know if I'm showing that right. Like k, what I'm saying is k is the largest power of 3. Maybe that's just the way to say it. So k is the largest power of 3 less than or equal to n. I actually, this is probably not right, but this is what I'm trying to say. There's some math person, I'm sure, that can tell me exactly how you describe that in mathematical notation, but that's what k is, right? So for example, 1 is always going to be 1. It's going to reset it 2 goes to 1. This one should be 3 though. So it probably should be that. Yeah, okay. The 2 is a weird case. I don't understand what. Well, I probably will once I figure it out. But so here's the 3s, right? Maybe more succinctly, like here's the 3s. We know that 3 wins. That is, if you're an actual power of 3, you win. If you're not, you increment until you get to 3. And then after you get to 3, you you do every other one. And it probably is more clear in the 9s. So you see in the 9s, you do 1 to 9. So you just count up if you're less. That is, you just do n minus k. But then if you're greater than k, you're some mathematical formula for this. And so that's where I think I'm at. Is I think I can, what I do is I solve for k. I'm probably not even using the, yeah, I solve for k. And then if k equals n, I return n or k. If n minus k is less than or equal to k, I return this, right? That's what I'm saying. N minus k is less than or equal to k, I return n minus k. And so now I just need to solve this last one. Yeah, is that always the case? It does look like it. And we go to 27, and then once you hit 27, you start like incrementing by twos. Nineteen minus 9 is about 20 minus 9. That's a little bit easier math. Is 11 plus 2. 21. Trying to see if there's a pattern. It's this number plus 1, or n minus k plus 1, n minus k plus uh, 2, n minus k plus 3. Is that right? No. Well, sorry, I'm just staring at this trying to find a pattern. It's like what if I double double 3 double it would be 1 2 3 doubling. No. 2 40 minus 27 is 13. Oh, what is that? 40 minus 30. 40 minus 37 is 2n minus 3k. 2n 19 times 2 is 38 minus 27. 11. Ooh, is it 2n minus 3k? Uh, hmm? Oh no, it was no, it wasn't it? Oh, these are the below ones. These are the bad ones. Like then these ones I want to ignore until I get to here. And then it works. Okay. I think that's right. Yeah, we ignore these until we get to 27. And then the question is at 27, do we now get the right numbers? Yes, we do. Okay, so I actually think we got it then. So the answer is this. And then we say so that's the k value. And so we say if input.len equals k, we just return k. Else if oh no, did I lose it? It was if we were less than k. Fucker. I've forgotten it already. Okay, so we'll do it right here. So let we'll say if let s equals if k equals I. We want it's just going to be I. Else the answer is so like in the nines, it's going to be 1, 2. It's it's else if n minus k is less than or equal to k. It's going to be n minus k. Oops. Else it's going to be 4 times I minus 3 times k. Right? I think those are the ones I have. Yeah. So let's make this S. Like that. Oh, N is I in this case. So I want the last numbers to be equal. Yes, 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 yes. Does not work for 7 or 8. 9. Oh, it wasn't 4 times 3. It was, wasn't it? Where did I put R3? R2, wasn't it this? No. What was it then? Bugger. Okay, let's figure it out again. These are right when we're lower than or equal to. But once we get above it, it's 19,911. So it was double I minus triple. Yeah, okay, so or yeah, so this wasn't a 4, this was a 2. Should be that. There we go. Okay. Okay, so this is the answer. So we'll do this, this, this. Let I equals input dot line. Oh, I is actual input in this case. Okay, looks good. So I remove this now. And put input here. I don't think I have resolution smaller than nanoseconds. So I think this is like, it's not actually 0. It's because I'm on a Windows box and it doesn't give me the resolution I want. Or it doesn't always give me perfect resolution. Ha! Okay. Okay. I know it's only been 30 minutes to you in this video, but that's like 3.5 hours. Okay, so what are the lessons here? First of all, apparently I need to fix my computer because it totally just blows up if I try and run the CPU at 100% for an hour and a half. Second, yeah, I sometimes you just got to look at the puzzle input. In hindsight, I probably could do the same thing in part 1 that I did in part 2 when I'm like looking for patterns. The problem was is part 1 just finished fast enough. So I didn't ever feel like, oh, I need to I need to find some pattern. But now knowing the Josephus, I probably heard this before somewhere. I just don't remember where. But that being said, like now you know, I know a Josephus problem, that helps. What else? Yeah, just look for patterns, right? And you can kind of see him, like maybe if I put this at the end here for a second, just so you can see. Like, think about what I was doing. When I first started, I just looked at n and the solution, and you immediately see, oh, 3s match up, 9s match up, 27s match up. And then I was like, okay, so what's the next one? 81. There you go. So it was clear it became like a pattern, right? So you have to say to yourself, okay, now how do I solve this pattern? And that's when I started looking. The next thing I noticed was this one. This one was funky. It didn't make sense. It was this first one, this pattern right here, where I was like, oh, look, when it hits 9, it then starts incrementing by 2, like every other one. And the what followed from that was, oh, well, I'm in the 9th K, so that 9 must be something interesting. And then that's when my computer blew up and I started looking back at it. But then I think what came from there was not, you have this delineation of 9 as the K value, whereas when it's above, it's just incrementing, or sorry, yeah, when it's below, I guess 9, below K, you're just incrementing. Otherwise, you're doing this thing, and I just had to figure out what those were, right? When you're incrementing, it's clearly just I minus K. This one took a little bit more to figure out, right? I think at first I was like, oh, this minus this plus 1, and then this minus this plus 2 doesn't work, because it's like, oh, it does work, 13. This minus this plus 3. Does that work too? For some reason, I didn't think that worked. What is that? 12 plus 3, 15. Oh, okay, so it does work. But you'd have to know, is this answer the same thing as... So let's say if you're 20, this minus this is 11. How do I know if I'm 0, 1, 2? It'd be this minus this. Because it's incrementing, I don't think you can figure out. But I did eventually get there with the... So what you usually do when you're looking for patterns like this that sort of fit is you just start like multiplying numbers, adding them, subtracting them. Fortunately, this one was a low one and it came through. If you can't do it that way, there are some things you can do that will help you like find patterns. But like you can see here, it's like it's clearly you double this one, and so that gives you 40. And then the question was, okay, well, 40 minus 13 is 27. And I'm like, oh, 9 times 3 is 27. So is it 2n minus 3k? And that turned out to be the right answer. I don't know how I got 4 down there. It must have been something weird. Anyway, there you go. So I'm very excited that I solved this, but it was one that was like, Um, let me get rid of this. Sorry. It was a long time in the making. I think we're like 3 hours in easily. Yeah, because this has been 40 minutes. I guess I spent a little bit of time explaining it to get me there, to get me to where I was. But I was like 2.5 hours in, and I guess if I didn't die, I was maybe like 10 to 15 minutes from a solution, because I had essentially figured out this and this, but I hadn't figured out this, I think, is where I left off, where I picked back up. Um, so that got me there. Anyway, crazy day. And this happens sometimes. It's possible that, man, I kind of want to be done with this day, but I'm curious how some people solved it back in the day. Back in the day. 5 and 4, the title lose the Josephus problem. Yeah, I didn't catch this first. I'm almost sure I do watch a lot of number files, so I've probably seen the Josephus problem before. It just didn't like trigger in my mind. I think I've said this before. It feels like I've forgotten more things than I can remember, so that's a weird saying. It probably applies to everyone, right? There's a cool trick for part 1. Simply convert the number to binary, drop the most significant, append it as a new least significant, and you're done. Oh. Is that faster than this? My solution, this right here, I got from the Wikipedia. It was like, can you get the highest ones bit? You subtract that from n, and you get this. By the way, again, that was all while I was solving part 2. Part 1, I had essentially solved naively. Not essentially, it was naive. The best I could do was ON squared. Remembering number files approach. I gave up on solving my input by force. And I just looked at the patterns. The pattern became obvious. And then just solved my input by hand. Yeah. Okay. Yeah, that's true. Once you've if you see this pattern, you could probably do this by hand and just put the number in, right? I mean, by hand is a little weird. How do you find the power of 3? I guess you just keep multiplying by 3 until you get there. Okay. It sounds like you're allowed to. Yeah, it gives you logarithmic time support, removing elements in the middle. So my guess is it looked like he was just doing the naive solution, but he found some data structure that allows you to do the quote unquote remove efficiently. Yeah, I think it's this tree stuff you do. You do it as a tree. Sorry, I'm just reading this. 46 parts for part 1. Oh, this is an interesting approach. Keep you start with the elements less than what you'd remove, and then everything above it, but a pinned left in reverse. So like for n equals 5, it'd be 1, 2, 5, 4, 3. Remove 3. Take 1 away and put it at the front of right. So you now have 2, 1, 5, 4. 2, 4, 1, 5 after this. So you now have 2, 4, 1, 5. Right pop 4. So now you have noise right here. If left is greater than right, 2, 4, 5, 1. 2, 4, 1, 5. It would be this. You'd pop 5. I actually have no idea how that works. I'd have to look at that. I don't know how this solution works. Do a tree to do fast removals. Interesting. How does this work? Winner. I actually don't know what that is. There must be some other mathematical solution than the one that I found. This one works. I mean, maybe it works for all of the solutions. The question is like this number in the lower half of the n minus k. Because if it is in the lower half of n minus k, this totally works. There must be some math you can do here. This is really crazy. I don't know about this math here. Again, I don't know a lot about math. Sometimes I can find patterns like I did in the output. Oh, here's a Rust version. Blah. A lot of these old ones aren't around anymore. It would have been nice to see a Rust version. Oh, I've seen this number file video before, apparently. I'll have to watch it sometime. Causes Part 2. Oh, is this a faster way? Yeah. This is where my math flailing happens. You can do log n over log 3. And then that'll give you the power. You can do 3 to that power to get b. And then he just, yeah, solve it this way. Perfect. So I did it in a loop. He used the logarithm thing. I think the loop is, I mean, it's definitely not faster. I think these things are calculated in constant time. But the loop is so small. My guess is even for really large numbers, it's like never, the loop is never more like 10 or 15 or something like that. Okay, I mean, clearly someone has found some math ways like this one. That I'll have to read and understand. But okay, there you go. Yeah, I don't know any other. There is definitely a math way. I guess I just don't know what it is. I mean, maybe mine is the math way. It's mathish, right? Okay. Yeah, I don't know what else to say. This is where I got. This is what I did. Again, I'm like 4 hours solving, so I'm definitely done now. But there you go. Thanks everybody for watching. Really appreciate it, and we'll talk next time. Bye.